Okay, so I'll try to be quick. I'm going to tell you about some experiments and simulations performed by my students Vaibhav and Sayantan. Vaibhav is now a postdoc at University of Tokyo. So Rituparno was the inspiration behind our foray into simulations. He's my brand new colleague at RRI. So, okay. So, we make these colloidal particles called microgels in our laboratories. Microgels are like these 500 nanometer rasgullas that are made entirely of this polymer called poly-N isopropyl acrylamide. So, the reason why I call them rasgullas is because these are very porous, it's basically a mishmash, a ball of polymers, and when you put them in water, they absorb the water because of an interaction between the amide group in this p-NiPAM and the water. Okay, so they swell. So the particles, the colloidal particles that I'm going to tell you about, they are all swollen at this temperature. So what we do is we take a very low concentration of these colloid particles in water, and then we just cast a small drop, and then we look at the evaporation of this droplet, and these particles are amphiphilic, so they all come and kind of, they decorate the interface, and they make all these structures that we're going to try to understand. So there is another thing that we did, which is that we changed the stiffnesses of these rasgullas by adding more crosslinkers. So these are polymers. So you can basically connect them by using these crosslinkers. In this case, we've used a polar crosslinker called methylene bisacrylamide. And it basically, it just, you can make rather stiff particles and all the way to really floppy, deformable and compressible particles. So what you see here are some electron microscopy images. So this is the soft particles. So I don't know if you can really see it, but these particles have these core shell structures. So as you go to stiffer particles, the core becomes larger, and the shell, which is like the corona, okay, these are like polymer brushes, they become shorter. Okay, and so this is a cartoon of the particles that are decorating the droplet. And because these particles are deformable, so this is the interface. The particle, to reduce interfacial tension, it spreads out into a fried egg kind of a configuration. Okay, so I think I'm going to work these from there. So I'll just show you some self-assembled patterns with the softest particles. So the subsequent videos are at higher time, because as you can imagine, as time goes, the solvent evaporates. So the area fraction of the particles at the interface becomes higher and higher. So this is the experiment. So we have the 63x oil immersion objective. This is an inverted microscope, and then this is our plane of vision. So we are looking really, really close to the interface, actually really close to this point, which is called the triple phase contact point. Okay, so this is at the lowest area fractions for soft particles. So you get these low surface density colloidal clusters. Some of them actually coalesce. I'm going to play them very fast. And then as the solvent evaporates, so now your areal density of the particles is higher. Okay, I'm not sure what that was. But then you see these voids, you see these foam-like clusters. Okay, and they are kind of decorated by these microgel walls. And then as solvent evaporates even further, you get these hexagonal lattices. Okay, and just a couple of takeaways from here. If you look at some of these structures here of the particles here, you see that the average distance between the particles is greater than the particle size. That kind of tells me that there is some kind of steric repulsion going on. The fact that these particles are ordered, that tells me that there is some kind of a long range attraction. And given that, we have these particles at the interface deforming the interface, that must be capillary attractions. How am I doing on time? Okay. So now we have an intermediate density, intermediate stiffness particle. And there again, these are videos as the interface is, as the solvent is drying up at the interface. And initially, it looks a lot like the softer microgels. Then you get these very, very disordered foams. This is where it starts getting different from the soft particles. And then as the solvent evaporates a little more, you see that you start forming these chain-like clusters. There's also a lot of very exotic dynamics. Like here, you'll see these clusters within the void of the foam that kind of merges with the wall of the foam. Okay, and here you see a cluster within the void, and here you see a an ordered circular cluster that's actually coexisting with disordered chain-like structures. So these are for the stiffest particles. Nothing really interesting happened in the stiffest particles. So from the beginning, the stiffest particles from chains, you can see they are practically stuck together, right? So that tells me that there is some very short-range attraction that's really playing a dominant role here. As it dries up even further, you can see some of these chains are actually folding and interconnecting and, you know, forming more compact structures. And eventually, I don't think I have that video, but eventually these chains all connect to form a percolating gel-like network. And here there's some, you know, interesting snapshots from some interesting dynamics where you can see particles connecting, the chains connecting, and then the chains folding to form these compact structures. So what you see here on the left, okay, I think now I can go there. So this is basically reconstructed images using MATLAB and Elastic. So you'll see 3 panels here. This is for the softest particle, this is for intermediate, and this is for the stiffest ones. And these are color-coded according to the local bond orientational order parameter. Okay, and the fact that these, so there are these 2 axes here. So this is the volume fraction as a function of the distance from the apex towards the triple phase contact line, which is the corner over there. So here the concentration of the particles is the maximum because capillary, as the evaporation happens, the capillary attraction drives the particles towards this triple phase contact line. So there's a gradient of areal density here, and then there's another gradient of areal density that you see along the vertical axis that is driven by loss of solvent due to evaporation. Okay, and looking at these, and I do not have time, but then we can kind of guess what these interactions are, and I'll tell you about them. Okay, so we want an interparticle potential that's going to capture all these experimental results that we saw. So this is what we have. So this is of course a hard wall kind of a potential. So then we've looked at the physically meaningful interactions between the particles. So the long range attraction that is giving rise to the chains that I showed you for the stiffest particles, that we have captured using a hydrophobic interaction. So Rajesh, you had objected to our hard wall potential earlier, so we've made an improvement here. So thank you. This is at SRM, remember? Yeah. So then, yeah, so this is the hydrophobic interaction. So this is because the polymeric moieties have an unfavorable, you know, they don't react favorably with water. So this is a purely entropic interaction that basically makes all the carbon hydrogens of the particles stick to each other, and that's why you get some of the chains that I showed you. The steric interaction is basically the compression of the polymeric brushes. And then you also have a capillary interaction, the Cheerios effect, coming from the deformation of the interface. This gives rise to an effective attraction, and you have a dipolar repulsion. And when you put all these together, you get a double well potential. And clearly the structures that you form, this depends on the competition between these 2 length scales that you have here. And when you work out all the, so here, I mean, in our minimal potential, we didn't change most of the parameters except for the corona thickness. So that's the steric part of the interaction and the dipolar strength. So, and then we can pretty much reproduce all the structures here. There's something interesting that I put in my abstract, but I can't tell you about. And that is, we see this for the intermediate stiffness data, we see some kind of an order to a disorder to an order transition again. And we see some hope of seeing glassy physics in monodisperse systems using this experimental and simulational platform that we have. Thank you.